In this question, we're asked about two aldehydes, so that if we just remember that aldehydes are compounds with this group, with this carbonyl C double bond O and a hydrogen at the end of the chain that have the molecular formula C4. And we need to draw those two structures and give their name. So whenever we're asked to draw two isomers, the first one to draw is always the straight chain. So we put all 4 carbons in a row, put the aldehyde group at the end, and then put in our hydrogens. We can see that we've got 1, 2, 3. Sorry about that. 1, 2, 3, 4, 5, 6, 7, and the 8th one on the aldehyde. This gives us the right formula. If we had to name this, we've got 1, 2, 3, 4 in a row. Bute. Carbon-carbon single bonds, an, and it's an aldehyde, al. So butan-al. And then we need to draw another one. So we do need to remember that to be an aldehyde, we have to have this C double bond OH at the end. So when we're drawing a second isomer, try to reduce the chain. So it's a chain isomer. So we're going 3 in a row, and then we're going to put the methyl group coming off. And the only place it can come off is that middle carbon. And so we've got our other isomer. There are no other aldehydes than these two because we can't go to 2 in a row, and there's nowhere else to put a methyl group. So this is the only other one, methyl, and then 3 in a row, prop, AN because the carbon-carbon bonds are single, al because it's an aldehyde, methyl propanal. So one of the first things to do when trying to decide, which it asks us to do next, which NMR spectra is which, is let's just see if we can do it by counting the number of types of carbon, because these two structures are different, they may have different numbers. Now in butanal, each carbon in that chain is a different distance away from that aldehyde group, and so each one of these is a unique carbon environment. There are 4 carbon environments in butanal, so we'd expect to see 4 peaks, 4 different types of carbon. When we look at methyl propanal, we can see that we've got the aldehyde carbon at the end, and then the one that is adjacent to the aldehyde carbon is going to be very similar to that one in butanal. But then we have 2 methyl groups both attached to that C, and so they would be the same as one another because they're in the same environment. So we'd only expect to see 3 peaks. So from number of peaks alone, we're going to be able to work out which spectra belongs to which, but then we can do our work with the datasheet to assign the peaks properly, because this is going to often be a longer response question. You may need to write more detail than you think, given that you could just do this quite simply from the number of peaks. You may need to explain fully how you've assigned them. And so we're going to see that the first one must be butanal, so we're going to copy our picture. Let's see if we can do that and put it on here. I'm going to paste it in. We got our butanal with 4 peaks, and we can have a look if we can see which peak belongs to which. So let's get our highlighter back up, and let's see. Always start with the more interesting end, in this case the aldehyde end, and if we look, aldehydes and ketones are coming out 190 to 220, so our red peak is this one here. Then we've got this orange one, which lives next door to this superstar aldehyde. So aldehyde's right down at the end there, they're the superstars of this. And this orange one, it lives right next door, so it gets speciality treatment, 20 to 50, it's coming upfield from the other peaks. And then the green and the blue, actually quite hard to know which is which out of the 2 remaining peaks, because the green and the blue would both be of this type, like the 5 to 40 type. Now you could argue that you know that the blue one is further downfield, further away from the interesting, and the green one is nearer. But at this level, we don't know for certain because they're both in that range, so there could be either of those 2 peaks. So we can't assign definitely whether the left-hand one belongs to the 3rd carbon in the chain or the end carbon. In spectrum 2, if we look at our methyl propanol structure, sorry, we're struggling to copy that there. There we go, copy, and then we'll put it on here. Yeah, if we look at our methyl propanol structure, again, we can identify that aldehyde and ketone peak, 190 to 220, and that living next door to the aldehyde and ketone peak at 20 to 50. And then our final type here would be this 5 to 40 type, and we've just got 2 of them. The peak looks bigger on the spectra because there's more carbons of this environment, and it all matches nicely up with what we were expecting. So we've identified which spectra belongs to which, and we could list each peak in an exam. The one between 190 and 220 in methyl propanol is due to the aldehyde carbon. The next part of the question asks us to do some predicting, and we're being asked to predict how many peaks we'd expect the carbon spectrum of butanone to have. So let's just draw out but for AN, single bonds, make it a ketone, put the hydrogens on, and then let's look to see how many different types of carbon. Now we could easily be tricked into thinking the 2 next to C double bond are the same, but they're not, because one lives then more next door to some more carbons and the other doesn't. What we do know is that we've got an aldehyde or ketone carbon, 190 to 220, and then we actually got 1, 2, 3 other types of carbon. So in total we've got 4 peaks because all 4 carbons are different. And the question then says, could carbon-13 be used to distinguish between butanol and butanone? And although there will be some slight variations, what we need to appreciate is that both have 4 peaks, and both have the same functional group, the C double bond O aldehyde ketone 190 to 220. And so we would say the answer to this question would be no. And the stock exam answer is both have the same number and type of carbon environments. That's our second set of examples. Our last set of examples on carbon NMR is without looking at some spectra, just to predict some things. So it says nitration of methyl benzene. So you might want to rethink about what that is, but methyl benzene is a benzene ring with a methyl group on it, and nitration is the reaction that uses nitric acid and a concentrated sulfuric acid. You should know this mechanism, but we're going to be adding a nitro group, or substituting a hydrogen for a nitro group, and making some water in an electrophilic substitution mechanism. It's many steps. But it says there's 3 possible products. Now, the first one that I've drawn there is if I nitrate it in the 2 position comparative to the methyl group, you can see there, I've put it next door. But who's to say that it wouldn't go in the 3 position? It does say mononitro, meaning 1 nitro group. Who's to say it wouldn't go there? Or what if it went in the 4 position? So opposite the methyl group, then we've got 3 different possible products. And what we need to do now is look at the number of carbon environments that we could come up with. Now there's would need a lot of colours of highlighters if we're going to do this, but we can give it a try. So we've got the methyl group each time. Okay, and then we've got the carbon to which the methyl group is attached on the benzene ring. Now what we need to do is look at these benzene rings and see if there's any symmetry. And in our bottom structure, structure 3, we can see that it's symmetrical because the groups are on a plane through the middle. We can imagine drawing if we imagine drawing like a mirror line through the middle here, then the two orange ones would be identical, and then we might have like different colour, two blue ones there, and then we might have this like purple one here. And so in total we've got 1, 2, 3, 4, 5 different colours, so 5 different peaks. I don't want the pen on red. Okay, and the next one, we had our yellow and our green, but this is now not symmetrical. So if this is orange, the one opposite it isn't orange because of the nitro group. So then we'd have to keep going around. We've got a red, and then a pink, and then a different kind of green, and then a blue. And so we can see that we've actually got 7 different colours there. And that's going to be the same scenario on our other structure as well, because as we go around, the nitro group is not symmetrical with the methyl, and so each one of these carbons is different, and we have 7 carbon environments. So could carbon-13 spectroscopy be used to distinguish between the 3 isomers? Well, we could tell isomer 3 apart from the others, couldn't we? Because it's only got 5 peaks. So carbon-13 NMR would be able to distinguish isomer 3. But isomers 1 and 2 have the same number and type of carbon environments. And so just like our previous question, we wouldn't be able to tell them apart. The reaction then also can produce di and trinitro products. This means putting 2 nitro or 3 nitro groups on. And we have to deduce the structure of something with 5 peaks. So bearing in mind we know that there are 7 Cs, if there are only 5 peaks, there must be some symmetry in this molecule. So remembering that we already had a methyl group, we want to put 2 nitros on this symmetrically. So if we put one here, we'd have to put one here. If we do that, we will end up with 1 for the CH3, 1 for the C next to the CH3, and then these 2 will be identical, these 2 will be identical, and that one will be different. And that would be 5 peaks. If we were to put them, there is another right answer, because if we were to put them symmetrically about this point, then you would get the same peak distribution in terms that you would get 5 peaks as well because of the symmetry around the methyl group. Now if we want to get 7 peaks, there are 7 Cs, we just need every C to have its own peak, so we need it to not be symmetrically arranged about the methyl group. So there are lots of right answers. It could be like this with the 2 NO2s next to each other. That would be one right answer, or you could put one here and one here, or you could move this one round one more. Basically, any 2 places that aren't the 2 in examples in answer to part 1 would be correct for answer to part 2, because every one of the 7 carbons would be different. If we want the trinitro, 3 NO2s, but to have 5 peaks, we need the same thing. We need it to be symmetrical around the methyl group. So we've got our methyl group. We could go 2, 4, 6. That would be symmetrical. There's one other way to be symmetrical. We could go 3, 4, 5. Sorry, oops, we're on the rubber, not the pen. So we could go here, 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 and we would be symmetrical as well. 2, 4, 6, much more likely than 3, 4, 5 though.